We have another problem here. Skater, initial speed, stops propelling himself and begins to coast across the ice. So some sort of ice skater, and I don't draw people well. This ice skater has been pushing himself along. At the moment the skater has this speed of 7.6 meters per second, he stops pushing against the ice, begins to coast, eventually coming to rest. So continues sliding across the ice in my picture to the right and eventually comes to rest. Air resistance is negligible. They give us a coefficient of kinetic friction. We want to know how far this skater will travel before coming to rest. So being given distance, being given speeds and wanting distance, that leads me to wanting to use kinematic equations. That's what we've talked about in terms of motion. Distance, speed. If I say his initial position is 0, his final position will be this distance d that we're looking for. V initial, 7.6 meters per second, comes to rest. So there has to be an acceleration, right? His velocity is changing, so there's an acceleration making that happen. We don't know the acceleration, we don't know the time, and we want d, that S final. Excuse me. So big three, the equation without time, since we don't know that either, that's going to be 0. I can bring the V initial squared to the other side. We know V initial, but to solve for this delta S will be d. To be able to solve for d eventually, we need to know the acceleration. Well, the acceleration is a result of a net force. So we can come back to what we've been looking at. We know that acceleration is net force over mass, or net force equals mass times acceleration. Both equations are the same. Well, we can set up Newton's second law for this problem to relate the forces on the ice skater to the acceleration. So free body diagram, always free body diagram. mg, force of gravity, that points straight downwards. The ice skater is on a surface, so there's a normal force, the surface pushing up against the skater. There is friction, there's kinetic friction. In my picture, I've drawn the ice skater traveling to the right. That would lead me to draw my kinetic friction to the left. Kinetic friction force always points opposite to the motion. He's not propelling himself anymore, meaning he's not pushing against the ice to keep going. And so this here is our free body diagram. We want to write out net force equals ma for both the x and the y directions. All right, so I'm just typical Cartesian coordinate system, x direction to the right, y direction up and down. We know there is an acceleration in the x direction. In fact, according to my picture, we should be able to recognize that the acceleration points to the left. It needs to be opposite the velocity to slow the ice skater down. I'm going to go ahead and call right positive x, So when I come back to my free body diagram, the only force in this case that's in the x direction is the force of friction. So I'm going to say minus, so negative force of friction, because that points to the left. Those are the only forces that I have in the x direction. That needs to equal the mass of this ice skater times the acceleration of the ice skater in the x direction. That is the same as the acceleration of the ice skater when we come back to our list of variables for the big three, for the kinematic equations. When I set up this table of variables, I was looking at motion to the right being positive, which is why I need to use motion to the right being positive in F equals ma. I need to make sure I'm accounting for the directions the same way. In the y direction, we know there's no acceleration in the y direction. It's not accelerating up into the air or sinking down into the ice. So those forces in the y direction need to balance out. I'm going to go ahead and combine. We know the force of kinetic friction is equal to the coefficient of friction times the normal force. So over here on the left, where we have the force of friction, I'm going to plug in coefficient of friction, but according to the y equations, the normal force needs to equal mg. So I'm plugging in what I know for the force of friction, and that has to equal ma. This is another situation where they did not give us the mass. But now that we have pulled in and written the friction force in terms of mu and the normal force, if we divide both terms by m, they cancel. So we don't need to know the mass. This tells me that the acceleration of the skater is negative mu times g. Now again, the negative sign is the direction. It points to the left. We've been given mu, we know g, so we can calculate what this is. The skater's acceleration is going to be negative 0.98 meters per second squared. So again, the negative simply means to the left. So now I know, oops, not 9.8. Now I know this acceleration that the skater's experiencing, and I can finish and solve for d. We knew the initial speed, 7.6. That needs to be squared. Divide by 2a. The negative signs are going to cancel. And I'm getting 29.47. So coming back to the problem in terms of significant figures, the 7.60 is 3 significant figures. The 0.100 is 3 significant figures. So my answer should be in terms of 3 significant figures. So the skater will slide 29.5 meters across the ice, assuming, of course, there's that much ice to slide across.